Magnets are the only objects that can stick to your fridge times and times your understanding of physics until you ask one tiny follow-up. Why? Like, really, why? Sure, we've got words magnetic fields, electron spin, very official, very confident. And then physicists quietly change the subject, like you just asked them to explain taxes at a party. Somehow, tiny charged particles line up, and boom, your grocery list is defying gravity. But what's actually doing the pulling? Is it a force? A field? A cosmic conspiracy of electrons? Today, we're diving into the awkward truth. We're incredibly good at using magnets, and a little suspiciously vague about why they work at all. Magnets are basically electricity's weird side effect that never left the party. At the most basic level, every magnet owes its existence to moving electric charges, because when charges move, they create a magnetic field. That part, physicists will say with great confidence, you've got electrons orbiting atoms, spinning like tiny charged tops, and boom, magnetism. But then you ask the extremely reasonable follow-up. Okay, but why does moving charge create a magnetic field? And suddenly the confidence drops from textbook certainty to, well, the equations say so. It's like asking why bread becomes toast, and someone just hands you a toaster manual. The real explanation lives inside Maxwell's equations, which are these beautiful mathematical relationships that perfectly describe how electric and magnetic fields behave. They work incredibly well. Engineers build entire civilizations on them. But they don't really explain why nature chose this setup in the first place. It's like discovering the rules of a game without ever meeting the game designer. So when you hold a magnet, what you're really holding is a chunk of matter where countless tiny moving charges are collectively producing a magnetic field, and we can predict exactly how that field behaves, while quietly accepting that the deeper why is still sitting in the cosmic suggestion box. Here's where magnets get even weirder. Inside a magnet, tons of electrons have something called spin. And when those spins line up, you get a magnetic field strong enough to stick your grocery list to the fridge. Sounds straightforward, like a bunch of tiny spinning balls all rotating in the same direction, right? Not quite. Because spin in quantum physics is not actually little particles physically spinning. If electrons were literally spinning like planets, parts of them would have to move faster than the speed of light, which is generally frowned upon by the laws of physics. So instead, spin is this intrinsic property, like mass or charge. It's just something electrons have. Calling it spin is basically a historical accident, like naming a massive continent, Greenland. It sort of misleads everyone forever. But mathematically, spin behaves like angular momentum, which is why physicists kept the name. When many electrons in a material align their spins, their tiny magnetic effects add up instead of cancelling out, and suddenly you've got a magnet. So your fridge magnet works because of a bunch of not actually spinning things aligning in a way that behaves like spinning. Totally clear. Completely intuitive. No further questions, please. You might wonder why everything isn't magnetic if all atoms have these little magnetic effects. Like, why isn't your spoon aggressively sticking to your phone right now? The reason is that in most materials, all those tiny magnetic contributions point in random directions and cancel each other out, like a room full of people all shouting different numbers. The net result is basically zero. But in certain materials, iron, cobalt, nickel, something special happens. The atoms interact in a way that makes their spins want to align with each other. This is called exchange interaction, which sounds like a polite academic term but is actually a deeply quantum mechanical effect tied to the Pauli exclusion principle. And here's the fun part. We can describe it mathematically very well, but explaining it in plain language gets fuzzy fast. It's like asking why a crowd suddenly starts doing the wave at a stadium. There are rules, influences, and probabilities, but no single, simple cause you can point to and say, that's it. In ferromagnetic materials, once enough spins line up, they create regions called domains, and if those domains align, you get a full-on magnet.